Okay, welcome back. So this week we have Neetu from IISER Bhopal talking about 2D droplets to 2D young wells. Neetu, go ahead.
Thank you. So I'm going to talk about the connection between unitary matrix models in 0 plus 1 dimension and 2D Young's theory. So the classical solutions of unitary matrix models, they can be thought of as some phase space geometries of a free fermionic system. And the analysis that I'm going to show is based on that description of the unitary matrix model. So now before I go into the details, let me just briefly mention about what people have done in this direction. So the main motivation to study matrix quantum mechanics comes from the fact that it has served as a successful tool to study lower dimensional bosonic string theories. And the connection between these two was made robust by Gross and Klebanov in 1991. Then Minahan and Polychronikos in 1993, they showed that the same matrix model can also describe a two-dimensional Yang-Mills theory with a compactified special dimension. So in this way, we can connect the two-dimensional bosonic string theory and a two-dimensional Yang-Mills theory. Then people further explored the connections between these two theories. Here's a non-exhaustive list of references. Then Minahan and Polychronikos in the same work in 1993, they also showed that the partition function of this 2D animals with a compactified special dimension, this can also be written as a one-dimensional unitary matrix model for both the UN and the SUN gauge groups. So the analysis we are going to do is based on like that will further show the connection between these two theories. So we'll be dealing with the unitary matrix model in one dimension. So here's a brief outline. So I'll first talk about the unitary matrix model and its free Fermi description. And we'll see that to look at the classical solutions of that matrix model, we just have to look at the Fermi surfaces of a free fermionic system. Then we'll talk about the fluctuations over those surfaces. We'll quantize the fluctuations and we'll see that the modes of fluctuation satisfy an abelian Kac-Moody algebra. Then we'll go on to constructing the Hilbert space of the algebra. And then we'll study the time evolution of states in that Hilbert space. And from the time evolution of those states, we'll reproduce the partition functions of 2D Yang-Mills theory on different Riemann surfaces. And we can also make a connection between the higher point functions in 2D Yang-Mills theory to the higher point correlators in the Hilbert space. And with some specific states, we can also reproduce the partition function of a q-deformed Yang-Mills theory. Now the 2D Yang-Mills theory, it factorizes into two sectors, a chiral and an anti-chiral sector. So we'll get those two sectors separately, and then we'll see how in this Hilbert space formalism, we can join those two sectors to get the full partition function of the theory. And for that, we'll need composite representations. So I'll introduce those and we'll see. So let's start with the unitary matrix model in one dimension. So this is how, can you see my cursor?
Yes.
Okay. So this is how the partition function looks like. This W of U is some generic function of unitary matrices U. So in 1978, what these people showed is that this model is equivalent to a theory of free fermions moving on a circle with this particular Hamiltonian, and the eigenvalue density of these matrices goes like psi dagger psi. Then in 1979, Javicki and Sakita, they showed that this model also admits a bosonic description as a collective field theory, where the collective field variables are the eigenvalue density rho and its conjugate momentum pi.
Neetu?
And
So in HF, is it W of theta or?
it's I mean, you can go to a diagonal basis and write it in terms of eigenvalues. So
Okay, I mean, I'm just trying to think. So for the Hamiltonian,
yeah,
so psi dagger psi you have written outside. So what kind of an object is W of U?
no, I didn't understand your question.
Oh, I mean, U I thought is something that has the description in the matrix model, right?
Right,
It's the unitary matrix.
right.
What is it in the free fermion theory?
So in free fermion theory, what you can do is, so if you write the Schrodinger equation, you can write a Schrodinger equation in coordinates, which will be the eigenvalues of these unitary matrices U,
Okay.
and then there will be a wave function which will be antisymmetric because this is a fermionic system, and that wave function you can relate to the eigenstate of the ground state energy in the matrix model.
Okay.
So I mean,
Mm-hmm.
there are a lot of details while
Okay,
going
fine.
from this to this, but
Okay. Yeah,
this is
fine. Okay.
roughly what it is.
Okay. All right.
But we'll see. I'll show, I mean, in a different way how we can see the description in terms of free fermions.
Okay, fine.
So
Okay.
I'm just not going to take this way of showing it. I'll take some other way, but we'll see how this is equivalent to a Fermi picture.
Okay, great. Okay, thanks.
Okay, so this HB is the collective field theory Hamiltonian. So let's first consider this collective field theory. We can write down the Hamilton's equations of motion. These are the equations, and as you can see, these are some coupled nonlinear partial differential equations, which are in general difficult to solve. So we introduce these new variables p plus minus in terms of rho and v, such that the equations are decoupled. So Polchinski in 1991, he showed the equivalence of these fermionic and bosonic pictures. He showed that the classical dynamics of these collective fields, it also admits description in terms of the evolution of free Fermi droplets. And we'll also see here. So let's consider a system of n free fermions moving on a circle. We can write down the phase space Hamiltonian. The term in red is the single particle Hamiltonian. This pi is the phase space density, which just incorporates the fact that the this fermion momenta lies between p minus and p plus. So p minus and p plus correspond to the lower and upper Fermi surfaces of the phase space. And then we can write down the Hamilton's equation, and it is very easy to see that these equations are equivalent to these equations for p plus and p minus. So finding out a solution of this system, which is given by p plus and p minus, is equivalent to finding out the lower and upper Fermi surfaces in the free fermionic picture. Then we can translate back to the bosonic variables with these definitions, rho and v. We have to do these integrations over the phase space density. And we can go back to the bosonic variables. So now we can take this Hamiltonian and do this integration over P with the upper and lower Fermi surfaces given by P minus and P plus. So the Hamiltonian will be given in terms of these variables. And if we just substitute P plus and P minus in terms of rho and V here, then we'll get back the collective field theory Hamiltonian. So we can see the equivalence at the level of the Hamiltonian as well. Now we want to write our equations of motion in terms of Poisson bracket, which we usually do. So to do that, we introduce these Poisson brackets between P plus P minus variables. So now that we know that we can consider our solutions to the matrix model as just upper and lower free Fermi surfaces, so we can study fluctuations about those surfaces. So let P plus P minus 0 be our classical solution. So we consider some fluctuations, which I am denoting here by P plus minus tilde. So we decompose our P plus P minus in terms of this classical solution plus a fluctuation part. Then these fluctuations satisfy these particular equations of motion. These equations of motion we can again get as Hamilton's equation from this Hamiltonian, and with these Poisson brackets. So now we can go to the quantization. So as we usually do, we promote our Poisson brackets to commutation relations. Then we do a Fourier mode expansion of the fluctuations. And if we just use these commutation relations of p plus p minus, then we can see that in terms of modes, they satisfy an abelian Kac-Moody algebra. So there's an assumption that we are making, so which is that the fluctuations don't change the area of these droplets. And this constraint implies that the zero modes of p plus and p minus, they are equal up to a sign. So for just notational convenience, I'm denoting it by pi 0. I hope I'm not going too fast. Is it fine?
Yeah, it's fine so far. Can you just go back to the previous slide for a second? So, so you had sort of classical. You had classical. So you wrote down one more slide back maybe. Okay, so what you've shown here is that you have a Hamiltonian in terms of these p plus and p minus variables,
Right.
And you've written down. You write down classical solutions. Then what you're doing now is you're looking at fluctuations about those classical solutions, and you're going to quantize them. Right? That's what's happening
Right.
here. Okay. And maybe can you go to the next slide? The form of this equation, the second equation from the top, right? The fluctuation satisfy. This is slightly different from like the earlier equation of motion, right? Because over there you had d theta hitting only one of the p's.
Right. Right.
That's just something that comes through algebra because you've
Yeah,
written
yeah,
out pretty much the same Hamiltonian.
Yeah, you just substitute this p plus
Just
as
into
p
that.
plus 0 plus h bar p tilde, and you'll get these equations.
I see. And can you show me the previous Hamiltonian? I see. Okay. All right. Okay. So it's not exactly the same because like yeah. If you go to the next one, I was thinking that p plus 0 takes the role of.
No, it's a little bit different.
Yeah, it's a little bit different. Okay. All right. Yeah.
Okay, so yeah, before we go to the construction of Hilbert space, I would like to mention a connection between this unitary matrix model and CFT on a cylinder. So here the classical limit is defined by this n goes to infinity and h cross goes to 0, so that n h crosses 1. So in this limit, these AKT and BKT, these are valid solutions of the equations of motion. So we can just absorb this time dependence in the phase factors, and then we can write the mode expansion of this p plus and p minus by introducing this variable z. And then we can compare this mode expansion with the holomorphic and anti-holomorphic conserved currents of a free bosonic theory on a cylinder. So this del phi and del bar phi, this is how the mode expansion of the currents look like. So this p plus tilde over z has a similar mode expansion to del phi, and similarly this del bar phi. And so these holomorphic and anti-holomorphic conserved currents are the primary fields of this theory. So just by looking at the mode expansion, we cannot say that these are some primary fields of a conformal field theory. So to justify or to sort of prove that they are indeed the primary fields, we need to calculate the OP. And if we find out the OP of this p plus tilde and p minus tilde, then we can see that it indeed has the form which the OP of this current should have. So they do behave like primary fields of a bosonic CFT on a cylinder. So next we go to the Hilbert space. So if we write down the Hamiltonian in terms of these modes, then the Hamiltonian factorizes into two parts, H plus and H minus, where H plus is given completely in terms of the modes A, which are the modes of P plus tilde, and H minus, which is given completely in terms of modes P. Then further, this H plus and H minus, both of these have three parts, which is this H plus 0, which is completely dependent on the zero modes. Then there's this quadratic part. And then there's this cubic term, which we can think of it like a cubic interaction between the modes. So the zero mode.
And the expression for H minus is the same, which is A is replaced by B's.
Right. It's the same. So the zero mode commutes with all the other A's and B's. So we can construct our Hilbert space upon a one parameter family of vector, which are labeled by the eigenvalues of the zero mode. I'm denoting it by S. So all the positive modes, ANs and BNs, annihilate this state S. And the generic excited state in the Hilbert space, this is just given by these excitations over the ground state. So the Hilbert spaces will also factorize into two sectors, H plus and H minus. And this we can also see it from the algebra because we get two copies of a U1 Kac-Moody algebra in terms of A's and B's. So the full Hilbert space is just given by a tensor product of this H plus and H minus sectors. So we'll look at the analysis only for one sector, and then the similar analysis goes through for the other sector. So let's look at the plus sector. So let's first see what are the basis states that we can write in this Hilbert space. So first one is just a generic excitation over this ground state. So these states are eigenstates of the free Hamiltonian, which is just the quadratic part, but these are not eigenstates of the full Hamiltonian. So this is one basis. Then we can introduce another basis, which we refer to as the Young diagram basis. This I am denoting by R plus, and this has this expression in terms of K vectors. So this chi R plus is the character of the conjugacy class CK of the permutation group. And the advantage of this basis is that these states
Neetu,
are. Yeah.
Sorry, this is going a bit fast. Can you go to the previous slide? Yeah, so I was a bit confused here because your Hamiltonian H plus is like an interacting Hamiltonian, right? The modes are interacting with each other.
Right.
So usually when one constructs a Hilbert space or a Fock space, one builds up using the free part, right? Those are free particle states. But over here, I'm just a bit confused about how
I
this
think
happens.
that's what we do when we treat the interaction as a perturbation.
Right, exactly. So
But
we're
here
scattering.
we cannot treat this interaction as perturbation.
Okay.
So the one way to look at it is, so I'm introducing this basis R. So and I'm saying that this is the eigenstate of the full Hamiltonian, right? So if you look at the, so I have not written the exact expression of the eigenvalue, but if you look at the eigenvalue of the Hamiltonian in this particular state, then the part that comes from the quadratic part and the cubic part, they are of the same order, even in the larger limit. So we cannot treat one as a perturbation over the other.
I thought that there's a difference of h bar, right, in the quadratic and the cubic parts.
Yeah, but no, but this also goes like h cross square.
I see. Okay.
This is a bit like the CFT Hilbert space, right? When you have Kac-Moody algebra,
Yes,
like Hamiltonian, you'll get by Sugawara construction, and
right.
And you construct the Hilbert space non-perturbatively.
Right. Yeah, this is similar to that. Should I go on?
Yeah.
Neetu, So why do you get a U1 Kac-Moody algebra? Because it seems like for any unitary model,
Yeah,
you'll get the
yes.
same kind of Kac-Moody algebra. Is there some
Right.
understanding?
I cannot think of
It happens to be so. Is that?
Yeah, I mean, if you take any generic unitary matrix model, this is what you will get.
Right. So what I was thinking is with some other algebra, we can't work backwards and get some other matrix model, right? We'll probably get a theory which is not equivalent to unitary matrix models.
Yeah, at least for one placket model, this is what we get. If we take some other matrix model, then I don't know. I'm not sure.
So, Subbu, can I say your question slightly differently? Are you asking like the dependence on the potential of the matrix model seems to have completely disappeared here? Is that?
Yeah, I mean, what I was trying to think is I was trying to think the other way around. Like in 2D CFTs, you have like you can have various Kac-Moody algebras corresponding to various groups with various levels, right? And you can construct a Hamiltonian and build a Hilbert space with each of them, right? So here it seems like only a particular quantum mechanics is related to matrix models. So I was just curious, if I take something else, like why does it single out this one? I mean, I don't know if that is a nice answer or anything.
Devanshu, do you have something?
Actually, if I may interject here, there is actually, I personally don't have a good understanding why it always turns out, but exactly as Madhu said, it does seem that, so there is a slight assumption here that the potential we have taken is a polynomial. So at least for that class, we do indeed will end up with always a U1 Kac-Moody, and this particular phenomena seems to be pretty generic.
Right.
And I don't know if she will talk about this, but even if like your Fermi surface continues to have multi-valued solution, like even for folds, the fluctuations, provided they are much lesser than the size of these folds, even those fluctuations will also have a Kac-Moody algebra.
I see.
Yeah.
So it's very generic.
The reason I'm surprised is because if I just forget about time, okay, I just look at so you forget the u dot square term, okay, you just have an ordinary unitary matrix model. Then the profile of the eigenvalue distribution is very is very sensitive to the potential that you're using, right?
Right.
The only thing that's universal is the edge behavior, which is always of this what is this form, this Wigner-Dyson type
Right.
stuff. So I'm a bit surprised that once you go to a quantum mechanics, that somehow that all goes away. But maybe that's not.
I won't say it's about more about. I think if I go to the large n limit, that's where probably the subtlety come in.
But then, I mean, even with unitary matrix models for, let's say, some polynomial potential, I mean, we're always solving it in the large n limit, right?
Right. I understand. Okay.
But there also we will get this algebra.
The thing is, no, so even there also I think, yeah, because in the sense that the problem with not having time is that we would sort of have to force in like sort of introduce a parameter, because ultimately we have to write down some kind of a phase space picture, right? So we need to introduce some kind of parameter which will work like a time, and we have to study evolution with respect to that. So in fact, in the last work,
there's no time evolution in the ordinary matrix model story.
So we sort of have to introduce it by hand, and in that context, if you do see, you will again actually recover back, which we did in our last work. I mean, I don't know. In the last work, we actually showed that even there also you end up with a U1 Kac-Moody. There we also had a Sugawara-like construction.
I see.
So, okay, I see. Okay, fine.
Yeah.
Thank you.
Should I go on?
Yes, please.
Yeah. So these states R plus, so any of these states R plus, they correspond to a Young diagram with the total number of boxes given by the sum over nkn. So, and as I said, the advantage of using this basis is that these states, they are an eigenstate of the full Hamiltonian with an eigenvalue which in the large n limit becomes equal to the quadratic Casimir of un. Then we can define coherent states. So this is how the coherent state looks, and we can write it in either of these bases, the K basis or the R basis. This SR plus is a sure polynomial, which is nothing but the character of a unitary group. And by definition, tau plus is an eigenstate of this annihilation operator an. In this case, the eigenvalue is given by tau n over h bar. So once we have defined our states, now we can define a mapping between the states in the Hilbert space and the Fermi surfaces. So this is how we define the mapping. Given any state psi, the Fermi surface, the shape of the Fermi surface is given by the expectation value of P plus operator in that state. So if we find out the expectation value of this operator in ground state, it turns out to be this value. So till now, whatever I have said, there's no need of taking any particular potential or classical solution. But when we are writing this mapping, and when we have to explicitly look at the shape of the Fermi surfaces, then we have to decide what is the initial classical configuration we are taking. So here we are taking a constant potential, and in that case, the minimum energy configuration is just given by P plus minus 0 equal to plus minus half. So this half is the classical configuration, and there's this constant shift of S in the in this so over the classical value. And if we calculate the dispersion in this state, then it turns out to be 0. So this ground state this corresponds to a constant shift over the classical Fermi surface, and we'll get the same shift from the minus sector. So overall, the profile of the Fermi, this Fermi droplet doesn't change. Then we calculate the expectation value in a generic excited state K, and the expectation value turns out to be the same as in the ground state, but the dispersion in that case is non-zero. So those states corresponds to some order h bar ripples over the classical surface. Then we go to the coherent states. So this is how the expectation value looks like. So again, there's this constant shift over the classical surface. Then there's this order 1 piece here. So this is a classical deformation, and since even if we calculate the dispersion in this state, it turns out to be 0. So in that sense, we can call these states to be classical, and they correspond to some classical deformations over the initial classical configuration. So this is how these Fermi surfaces look like for these different states. So the first one is a profile corresponding to the ground state, and the second one corresponds to a generic excited state K, and this third one corresponds to a coherent state. Then we go to the evolution of these states, or correspondingly these Fermi surfaces. So the transition amplitude from any state, any initial state I to F in time t, we can, the usual way we write. And if we consider the evolution from a coherent state tau A to tau B, then we'll get the chiral partition function of a 2D Yang-Mills theory on a cylinder. These sure polynomials SR of tau A and SR of tau B, they correspond to the two holonomials defined at the two ends of the cylinder. Then we can take a particular coherent state which corresponds to all these tau wise variable which appeared in the coherent state. So these tau n, these are denoted by tau n here. So if I take all of these tau n's to be 1, then I'll get a specific coherent state. And if we consider evolution from that state to a generic coherent state, then we'll get the disk amplitude. And if we take both the initial and final states to be this state tau star, then we'll get the sphere amplitude. Now to get the partition
Neetu?
function, yeah.
Sorry, maybe I think that was a bit quick for me. So, like, can you explain why the chiral partition function of 2D angles appears? Like, it seems.
So
Where
right
does
now,
this come from?
yeah. So right now I'm just considering only one sector of the Hilbert space,
Mhm.
right? So in the okay, let me first ask you. So are you asking me about the factorization of Yang-Mills into chiral and anti-chiral sectors,
No,
or why am I
that part
getting?
is fine. Why is there Yang-Mills at all? Like, here.
Why is there Yang-Mills at all? That's what we are asking.
Yeah. Why does it arise in this context? Is there a way to understand that?
I mean, that is what we are getting. I mean, this is, yep. So we had a Hilbert space. We have defined some states. Now we can just study time evolution. I mean, in any quantum system, that's what we do, right?
Right.
So here what we see is that if we take this particular coherent state, then the time evolution just gives us the Yang-Mills, gives us the partition function of Yang-Mills theory.
Yeah, but
So
I mean, no,
the connection between these two already exists. I mean, people have talked about these connections. This is just another way of getting that connection. I mean,
I see. But yeah, I guess I'm asking sort of why does this connection exist? I don't know the story. So
okay, so even I don't know the details how people have shown, but most of the things, I mean, the in most of the literature that I have seen, so people show this equivalence of Yang-Mills theory and this unitary matrix model is at the level of the Hamiltonian. So here the more that we are doing is we are making a we have constructed this Hilbert space and we are making a correspondence at the level of the solutions, and we are saying that the evolution of these solutions also gives us the Yang-Mills theory. And the additional information, the other additional information here is that when people find out this connection between Yang-Mills and unitary matrix model, so they have to consider the theory on different Riemann surfaces case by case. But here we are getting all of these partition function, be it on a cylinder or a disk or a sphere, and even on a generic genus G Riemann surface from the same Hilbert space. So,
Neetu, can I say something?
sure.
In answer to Madhu's question, actually, Madhu, the connection exists through study of 2D bosonic strings. So this Hamiltonian that Neetu showed, A dagger A plus a cubic piece, A dagger M plus N. So you can show that in the context of 2D bosonic strings, this is basically the quadratic part is basically the free dynamics of a closed bosonic string, and that cubic part is nothing but the what is known as the splitting joining interaction. So first people map this H plus this Hamiltonian to this 2D string Hamiltonian, and then there is a map between 2D bosonic string theory and 2D angles. So this is how the mapping is established.
I see.
This is actually there in the review lectures of Jevicki and Polychronakos and Minahan. So, but we don't talk about the 2D bosonic string theory part. We just we are showing a direct mapping, how to exactly interpret the quantities on the matrix model directly to angle. I mean, to 2D angles without going through any string theory, 2D bosonic string theory description.
I see. Yeah, but I mean, maybe.
You have some other question.
No, I'm just trying to understand where. Is it because if I have like so these unitary matrix models, they come from essentially. Okay, is okay, fine. Maybe this is it. That like these 2D matrix models, they just come from a Yang-Mills theory, right? They're like a sort of dimensionally reduced kind of version of 2D Young-Mills, right? That was the context in
matrix
which,
model.
right? Sorry?
You said two-dimensional matrix model.
No. Like two-dimensional Young-Mills. The context in which matrix models were originally developed is probably just this, right? That like you wanted to study 2D Young-Mills, and then you say, okay, fine, I'm going to just look at the theory in zero space-time dimensions, and that gives you the something like that, right? I think that's
Exactly. This is the Gross-Mathitsin work actually, Neetu, that
yeah,
Madhu
that's
is
it.
referring to.
Okay, all right. Okay, sorry. Yeah, fine. Okay, I understand.
So I just again, sorry, I think Gross-Mathitsin explicitly showed that the cylinder amplitude of 2D Young-Mills is exactly equivalent to, their paper has that details. So you're right, exactly in that context also you can think of it that it pops out from there.
By the way, is 2D Young-Mills is Young-Mills a propagating degree of freedom there?
It's topological, right?
Topological.
Topological, I see. So what are these like things that we are computing? Just the partition function.
Yes.
Yes.
And then
I
the
see.
higher point functions are just correlation functions of Wilson loop.
I see. Okay, so there is a topological theory and you are dimensionally reducing it, is it?
Yeah,
I mean,
it is something that at least in the string theory that's what people do.
I see. Okay, fine. Okay.
So is this part fine?
Yeah, I think it's.
Yeah, fine with me too. Yeah.
Yeah, so to get the partition function on a genus G surface and also the higher point functions, we introduce an operator O and a density matrix rho G. So now once we have this density matrix, we can find out the partition function, which is just given by the trace of this density matrix. And we can see that we get the partition function of our 2D angles on a genus G surface. And then if we take the ensemble average of n of these operators O, then we get the higher point functions in 2D angles. And these Schur polynomials, they correspond to the holonomies around, so taking n of these operators is like introducing n punctures on the Riemann surface, and these Schur functions, they correspond to the holonomies around those punctures. Then we can go to the q-deformed Yang-Mills theory. So for that, we define these new set of states which are labeled by a parameter q. This lies between 0 and 1. So, so this state in Q goes to one limit. This reduces to this special coherent state that we consider tau star. And the projection of these states along this basis R plus gives us the q-deformed dimension of the representation R plus. So we can expand these states in R plus basis, and then we can again find out the transition amplitudes. So if we consider the evolution from one of these q-deformed coherent state to a generic coherent state, then we'll get the disk amplitude of a q-deformed Yang-Mills theory. Okay, so till now, whatever partition functions we have got, so that just gives us the chiral sector of the Yang-Mills, and which it should be because we were considering on only half sector of the theory. So there's this minus sector. So we should get the full theory when we consider both of these sectors together.
Neetu?
Yeah.
Sorry, I have a stupid question. I mean, like I am getting confused because of this transition amplitude. Like it's a topological theory. So what do we mean by this transition amplitude?
So this transition, now we are completely in a different system. We are now in a quantum mechanical system of these free fermions.
Oh, I see. In that, okay, I see. Okay, fine.
So we are calculating transition amplitudes there.
I see. Okay, fine. Okay.
Yeah, so to get the full partition function of Yang-Mills theory, we have to join the two sectors, and for that we go to these composite representations. So let's say we have these two representations, R plus and R minus, represented by these Young diagrams. So to get a composite representation, there are two ways to do it. The first one is we can just put this R plus in the standard way, and then we can take this R minus, put it upside down at the bottom, and we have to make sure that the total number of rows in this diagram is always n. So that's a composite representation. And an equivalent way of drawing this Young diagram is this one, where what we have to do is we just place the conjugate representation of R minus in a standard way, and then place R plus again in a standard way next to that one. So this red boundary is the boundary of a Young diagram, which corresponds to the conjugate representation of R minus. So actually this last one was introduced first in the context of Yang-Mills theory by Gross and Taylor. And then this Aganagic, these people, they said that we can also draw these representation in this way. And in this way, it is, we can understand it, it in terms of the representations of UN as well. So if we draw the Young diagrams for a UN representation, then there are boxes which are placed upside down, which are termed as the anti-boxes. So in order to sum over all the representations of UN, we have to consider these sort of representations. So in that sense, it is natural to consider these sort of representations. So if we just consider the states in the full Hilbert space in terms of R plus and R minus, then they are just given by this tensor product. And we can write write the states in this composite basis. So this is the relation between the two bases. These n's are Littlewood-Richardson coefficients. So then we write a coherent state for the full Hilbert space. And we use this relation to do that. And here what we do is we introduce this composite Schur function for a composite representation, which is the product of individual Schur functions with this multiplicative factor, which depends on these variables tau a and tau b.
Neetu,
yeah.
So this composite representation, I'm a bit confused by the diagrams with respect to UN. Like what sort of tensors would you write for this, the thing in between?
Sorry, I didn't understand the question.
Oh, I mean, like you can write these tensors, which are like wave functions in SUN, right? If you have a box above and below, then you write, I think, antisymmetric, and horizontally, then you write
symmetric along the row and antisymmetric along the column.
Column, right? So what is this thing that goes to the left of the central line?
Oh, I don't know that.
Okay, fine.
Okay. So basically the second diagram and third diagram, the claim is that, okay, so firstly, the things on the left of the vertical line, they are said to have negative box numbers. So now this Young tableau, for example, so you should not associate an index structure to the middle diagram, but representation theory wise, the middle diagram is same as the last diagram where there is this red colored thing.
I see. Okay.
So with that, you associate a tensor structure, and you symmetrize, antisymmetrize with indices with respect to that Young tableau.
But what about the bottom boxes with like the dotted lines? Are those?
No, they are not there. I mean,
okay.
Yeah, they are not there.
I mean, you complete the rectangle, then you throw
this I've just I should have said this. So this I've drawn just to show how do we get the conjugate representation.
I see. Okay, all right.
Okay. You threw this whatever was there to the left of the central line.
Right. You complete the rectangle and then you throw away the original boxes.
Okay. Great. Okay. Thanks.
Yeah, so we can write this coherent state for the full Hilbert space. Then if we again consider a time evolution from coherent state tau A to tau B, we'll get the partition function of the full Yang-Mills theory on a cylinder.
Sorry, Neetu, what is in this composite Schur functions? So what is this tau A vertical tau B?
This is some exponential of these, I mean, some multiplicative factor which just depends on this parameters.
Okay, it's not like an inner product or something.
No, it's not an inner
It's
product.
just some
It's exponential of something.
I see. Okay, it's just notation for that. Okay.
Yeah,
Okay.
it's just a notation. Okay. Yeah, so that's all. Let me just summarize. So what we did is we took a bottom-up sort of approach to show a connection between the unitary matrix model in 0+1 dimension and Yang-Mills theory via quantization of phase-space droplets. Then we got the partition functions of two-dimensional Yang-Mills theory on a genus G Riemann surface through the evolution of these free Fermi surfaces. And then we also got the partition function of q-deformed Yang-Mills theory by the evolution of some special type of coherent state, which corresponds to some special type of geometries of the Fermi surfaces. And one thing to note here is that when we write down the partition function of a q-deformed Yang-Mills theory, the gauge group is deformed there. But when we are writing it from here, so on the free Fermi, when we are dealing with the evolution of these free Fermi surfaces on the matrix model side, there's no deformation of the gauge group. So yeah, that's an important point. That's all I have to say.
I don't understand the last point.
Yeah.
Can you say that again?
Yeah. So the point is when you say that you have a q-deformed Yang-Mills theory, what you mean is your gauge group is quantum deformed, which means if you consider a matrix, say your gauge group is SU2, so you consider a 2 cross 2 matrix with elements A, B, C, D, then those elements will be non-commuting. So,
right. It's basically just the SU2Q, right? Where you sort of deform the Lie algebra, essentially.
Right. So there's a deformation of the gauge group. But when we are studying the evolution of these Fermi surfaces, the group is still UN. It's not UNQ.
I see. Okay. All right.
So although
but then in your coherent states,
hmm.
in your when you define the coherent, here q-deformed coherent states.
Hmm.
Oh, I see. I see. Okay. All right.
Yeah, the basis still is R plus. There's still the representations of unitary group. There's no deformation of the gauge group.
I see.
That's what I meant.
Is it obvious that you'll get the same thing, like in the end?
Sorry, what?
And like if you sort of if you define your coherent states like this, and then you still work with the R's are representations of UN, right? Not quantum UN.
Right.
Then is it obvious that the end result will be sort of amplitudes for q-deformed Yang-Mills?
Yeah, this is what we have explicitly seen.
No, I'm trying to understand if before you compute it.
Okay.
Is it obvious? Sorry, maybe that's a weird question.
I think because we are just changing the coefficients here. The states are still the same.
Right.
So even even when we write a coherent state with the coefficients we introduce here, these are just some generic parameters.
Right.
So that's what we have done here. So as such, I mean, there's no reason to expect that something is going to change or the representations are going to change.
Okay, okay. Yeah, I'm just trying to see if like if it's obvious that you're going to get an amplitudes for q deformations of Young's theory when you make this change. But yeah, maybe that's not a very good question. Never mind. It's fine.
I think this part is important here, this inner product. Since this is giving us this q-deformed dimension, that's why we are getting the partition function of q-deformed angles.
I see.
So if we make some changes here in the coherent state, then this won't hold.
I see. Okay. Okay. I understand. Okay. So this is, okay. This is very important then, because that's what's ensuring that your transition amplitudes from these coherent states. Okay. I see. All right. That's good. Yeah, okay. Thanks.
Anybody have any other questions?
That's my line.
Yeah, I was thinking.
No, so your talk is over.
Yeah.
Wonderful. Okay. All right. Let's thank Neetu for that very nice talk. Okay. Maybe if there are some questions, we have some time for questions.
So Neetu, so this is a different way of seeing the map that already existed, or like the q-deformed map did not exist?
Yeah, this q-deformed, at least as far as I know, I haven't seen this map between the q-deformed angles and
I see. Okay.
Matrix quantum mechanics.
Okay.
It's pretty neat, right?
Yeah.
Works out very nicely.
Yeah.
Yeah, and the important thing is that this Hilbert space has a lot of information. I mean, you take any Riemann surface of any genus G and you can get the Yang-Mills theory from just by choosing some particular states.
Right. So these states, to a guide to get them is this equation that you were showing, Madhu, is it, or like do you have some other guiding
guide
principle?
To what?
To write this state, right, so that you get the thing for a particular Riemann surface.
These particular states are defined to get the partition function for q-deformed angles.
Okay.
And I defined these other coherent states, these ones. So from these states, we get the ordinary Yang-Mills theory.
I see. In different,
yeah.
I mean, what do you have to do to get different
so here,
Riemann surface?
Yeah. Sorry, so here, for example, if I take two generic states, tau and tau b, I get a cylinder amplitude. Then there's this specific states which corresponds to this a specific choice of these parameters tau n. Right? These are some arbitrary parameters.
Okay.
So if we choose all these to be one, then we'll get a specific coherent state, and the evolution from that state to a generic coherent state will give us the disk amplitude.
So this thing, so these are observations, or like given a Riemann surface, you knew like how to go to that?
No, these are observations.
Okay.
One small thing I wanted to add. So she mentioned about disk and sphere. So you can also, because you need 3 building blocks for a generic Riemann surface. 3-point correlators will also give you bands. We also have computed 3-point correlators.
Okay.
Right.
So then if you wanted to build up a general Riemann surface, then you just do the pair of bands decomposition and then you compute inner products in the usual way.
Exactly. We I mean, the same holonomy swing and stuff. So yeah, we can do that also.
I see.
Yeah, for example, to get the partition function on a torus, we can just take the cylinder partition function and then we can identify the two ends. Do a search the end, get the partition function for a torus.
Okay. Yeah. So now that you have it, it's very powerful. Okay.
There is one actually, Zuhal in one of his notes wrote something. That has some dimensions and some equations. Oh yeah, that is the.
Okay. Any other questions? Maybe from Neetu's fellow colleagues at IISER Bhopal. No, nobody has any irritating questions for us, Neetu, now.
No, they don't understand what math is. I have defined that. Okay. Yeah, you have primary operator.
Okay. Okay. So if there are no more questions, then let's thank Neetu once again for a very nice talk.
Thank you for listening.
Yeah. Okay.